The purpose of this module is to introduce you to the use of differential equations in physics. So differential equations are at the heart of almost everything that we do in physics. So for instance, in mechanics, we are dealing with Newton's second law, which is a differential equation. We have the force equals the second time derivative of position. And when you do other kinds of physics, the same thing holds true. So for instance, in quantum mechanics, you're going to be dealing with Schrödinger equation, which is a differential equation. If you continue taking quantum mechanics, you will eventually encounter the Dirac equation, which is also differential. In E&M, everything you do is based on Maxwell's equations. And if you're interested in doing, for instance, general relativity, well, then you have to deal with Einstein's field equations, which are partial differential equations. And the same thing holds true if you're doing, let's say, I don't know, fluid mechanics, where you're dealing with the Navier-Stokes equation, which is also a differential equation. And I can make a much longer list, but you get the picture. What we're going to do here is start to dip our toes into this very large ocean and show how we can use differential equations to come up with rather non-intuitive solutions to physics problems. Essentially, this is a two-step process. You start, put a little divider here. You start with a physics problem. Here's your physics problem. And you take this physics problem and you develop a physical model and you apply principles of physics that you know. That says apply physics principles. I'm sorry for the poor handwriting. This then leads to differential equations, which in mechanics we're going to call equations of motion. Those are differential equations. Okay. And then from those differential equations, you then attempt to solve. When you attempt to solve it, if you're lucky, you'll be able to obtain an exact solution. More likely, you'll be able to obtain an approximate solution, and there are various methods for doing that. Some of them are known as perturbation theory, which you will encounter in the second semester of quantum mechanics. And if that fails, you'll have to resort to numerical solutions, which gives you a solution for a particular case, but might not give you as much physical insight as you would like to. So then you also have the possibility of applying different kinds of analysis, which we will see next semester if and when then we cover nonlinear dynamics. Okay, so this will then lead then hopefully to a solution, which gives you, for instance, in mechanics, you might get the position of an object as a function of time, its velocity as a function of time, maybe some angles as a function of time. If you're working in electromagnetism, maybe you get an electric field, etc. So it's a two-step process. This is the first step. This is the second step. The first step is where most of the physics comes in, and that's really where this course is going to be most interested in working. You still have to be able to apply step 2. That's a lot of mathematics, but physical insight plays a role here too. In particular, if you do this correctly, you can extract some physical insight about the problem that we're studying. Now, in this model, we're going to follow this process in one particular case. And that's a case of projectile motion subject to air resistance. So we're going to spend a little bit of time on this, but what you should take away from that is not that air resistance is an incredibly important problem, although it is interesting, but rather you should try to extract this process so that you're able to apply it to other types of problems that are not related to air resistance, because this flow is going to be used throughout this course and also in other courses, quantum mechanics, electromagnetism, when you get to those. So let's now start by giving you a couple of examples of these type of differential equations. Now, if you've taken, as you should, differential equations, you know that there are many different kinds of them, and there are many different methods for solving them. For now, we're going to restrict ourselves to ordinary differential equations that are separable. If they are separable, that means that they are subject to solution through separation of variables. Or direct integration, which is essentially the same thing. This is something you've already seen in Physics 2305. The very first thing you saw, I believe, is this kinematic equation where you said that the second time derivative of x is a constant acceleration. Well, you didn't use the dot notation, but you were given this as a problem that you would be studying. At that point, you weren't actually asked to solve this problem, but you were just given the solution. But to solve it is relatively simple. We start out by looking at the velocity, v dot equals a. So that is essentially dv dt equals a. The idea here now is that we separate everything that has to do with time on one side of the equality sign, and everything has to do with the dependent variable v on the other side. In this case, that's very simple. We just get dv equals a dt, and then we integrate this. Okay, so we integrate it from the beginning of time, which we might call t naught, to the present, which we might call t. Now, if you call the present t, then we have an integration variable here, which is also t, and that isn't too useful. So we're going to have to call it something else. I'm going to call that t prime. So if this is confusing, imagine what we're doing is the following. We have here time t0, time flows, and at some point here we have time t, but in between we have time t prime. Just for the purposes of calculating what happens, it's time t. Okay, so we calculate from t naught to t, and we change the name of the variable in here to t prime, and we do the same thing for the velocities. Okay, and now we can just take these integrals, and we get this. All right. Now v is also the time derivative of position, so we get that x dot equals v naught plus a t minus t naught, and then we can do the process over again. So now x goes from x naught to x, t goes from t naught to t, and we have to change the name of the t here inside the inside the integral to t prime to distinguish it from the boundary. Okay, and then we just take the integral just like before, and it's a little bit of algebra, but we get is the following. And then conventionally we take that the initial time, t naught equals 0, so that gives us that, with which you're already very familiar. Right? That's the solution you were given in the beginning of Physics 2305. Okay, if you've taken this simplification in the beginning, by the way, it would have been saved some algebra. All this would have been unnecessary because we would have gotten this result already up here. You wouldn't have to worry about that square. Okay, so this is fairly straightforward. This was a fairly straightforward example, but it doesn't always have to be that simple. I'll give you one other example here that's a little more involved. Here is another ordinary differential equation that you can solve with separation of variables. Okay, so it may not be obvious that this is separable and that you can just integrate it, but it is. So let's write it like this: 1 minus kx times dy over dx equals 1 minus y squared. So the idea here now is that we want to put everything that has to do with y on one side of the equality sign and everything has to do with x on the other side. So we just have to divide then by 1 minus y squared and by 1 minus kx divided by dx. And then we get okay, and then we integrate this from y naught to y, becomes y prime squared there, and same thing on the x side there. Okay, so this is now something you can solve directly. It's not intrinsically interesting, but I'll do it anyway here to illustrate a few math principles that you should be familiar with. This integral is perhaps not something you can tell off the bat what it is, but you can look it up in integral tables, and you will find that this is actually the inverse hyperbolic tangent of a function, which we write as r tang. So this is r tang of y prime, goes from y0 to y. If you don't know what r tang is, if you're not familiar with this, you should look at the math interlude that deals with hyperbolic functions. You will need to be able to work with these type of functions soon. That also should be available in the math interludes module. And this is now, the integral of this is a logarithm. So you get 1 over minus k times ln of 1 minus k x prime, goes from x naught to x. Okay. This now becomes just r tang y minus r tang y 0. I'm going to leave that alone for now. This will develop a little bit here. And this you should know equals okay, and that in turn is equal to and then we can take that one step further. So this calculation here, from there to there, involves several logarithmic operations that you should be comfortable with. If you don't understand this, or if you don't feel comfortable doing this on your own, you should definitely review logarithmic algebra. Okay, that's something you need to be able to do. Okay. All right, so let's continue this for a little bit longer. And I'm just going to call this ln of k for reasons that will be obvious in a minute. And it's just a constant, so that's perfectly okay to do that. and then the rest is just algebra. I just discovered I made some mistakes here and put the knot in the wrong place. And let me just fix that quickly. Right there. Okay, so that went by pretty quickly, but really it's just algebra. Just to illustrate that, even though the method of integration is straightforward, the calculation efforts doesn't necessarily have to be. It also introduces a couple of concepts that you should know about the hyperbolic functions as well as logarithmic calculations, which you need to know. The important part, though, is that you're able to put it on this form, and then on an exam, if this were to come up, the getting to this point is the most important part. The rest counts for less points, even though it's more work. Okay, so this ends this video. In the next one, we're going to actually start doing some real physics and apply these type of differential equations to the problem of air resistance for a projectile.